Yeah.
And then I think moving forward for the end of the year, the three sort of like system-y courses that I'll be doing is there's one on so-called system dynamics, which is basically
dynamic. Yes, there's some fluctuation and time-dependent variables there. Yes,
exactly. And then the other two, one will be on information theory.
Yes, well, that's that's a theoretical part. Yes, yes.
Yep.
I think you are good. You are good at this. You are very good at absorbing these new ideas and terminologies. I think it's good. I think the trainer or the university side just want to make sure each student can speak in the same tone or same language, and that would be sufficient, yeah, for them to offer you the degree. And I think it's good. But in the meantime, I think it's good to know that the underlying ideas, yes. And
how do you think I should approach it this year? What do you think I should be focusing on?
I think I can read, but not too much, and perhaps just selectively. You don't because we have limited. Everyone have limited time, so you have to manage your time. Mm-hmm. And information technology, in my opinion, is just it's nothing exciting. I mean, it's just they probably over the past few decades, people come up some of the descriptions. So accept that. Okay, accept that.
Yeah.
Don't learn from me. I always argue with people.
Sure.
You just accept that which you sound makes which the interpretation consistent. Sounds good. Okay.
Yeah.
And don't go too far to the abstract discussing. And you just take the name. For example, if say, oh, say information entropy is the analog of the thermal. Accept that. There's no point to dig out more.
Yeah.
That's why I say. I think ultimately you're going to write a thesis, right? At the end of yes, and that's where probably you can. It's time to accumulate some reference. While doing my PhD, in those days we don't have much computer system. We have computer, but basically we got hard copies. I think on my desk got a huge amount of the photocopies of the papers. So it started earlier. It's good for you for writing. Okay, you have proper entry to search particular ideas and particular authors, and that would make your writing easier and faster. I spent 1 month actually. I spent only 1 month to draft my PhD thesis.
Really?
Yes, first draft. My supervisor was surprised.
That is quick. Yeah.
Yes, quick. But that's due to preparation. You see.
Of course.
If you have good preparation, you know what you're trying to say.
Rather than just one day. Okay, let's start.
Yeah. Oh, yeah. It's too late. It's too late.
Yeah.
It's too late.
Yeah.
Yes. So what do you want? Yeah. Any question? Any particular topics we can...
Well, do you know what? I was really enjoying our discussions of linear response theory.
Oh yes, we can continue that. Yes, we just have the beginning. Yes.
Yeah, because
you see, the linear series is a sound. Is based on the practice or some pioneers in physics. The unconsciousnly at the beginning to get this point, get idea. Actually, the derived result is pretty. At the beginning, the story is very simple. Let's go to whiteboard. Yeah, I probably just go. How do we show that? Okay. Yeah, I just repeats the same simple idea, right? So basically, where's my pen here? So the whole idea is the basic idea of the linear response theory is that we have a system in the box, have a system, and then this called the system. Because the system, it could be anything. Could be physical, could be subjective, quite subjective stuff. Like we say, for example, people study the human brain. For example, that's another is much more complicated than physics. the model in the physics 16. And so they got, of course, relatively speaking, this is external.
Yep.
Anywhere external. So if you have generated something, which can we call, did we call the F, right?
Mm-hmm.
It could be time dependent or could be the pulse, okay?
Yep.
So the generator is called a perturbation, or
Yep.
you can use P for perturbation.
Yep.
Obviously, you see, if you have observer here, they got something, all right?
Mm-hmm.
Anything you just, for example, when the sunlight passing through the glass of colored water, it changes color. Okay, it's pretty logical. See, the idea is very simple. So then they got observe, right? Now then, in terms of the formulation, in terms of mathematics, people were asked, well, how do we connect with these two? Okay.
Yep.
So basically, you remember that I copied that diagram here. That is so the idea is that observe this observed, this O for observation, observation, and then observation can be in general written as integral, right? So they have so that's why they got FT. Because they want to go to integration, they can use tau here. So this is actually in general is a function of time. So these were the to take into account that we have to we have introduced the chi. Okay, some people pronounce as a she. I don't know why. This is a Greek notation, a Greek alphabet, and then we have to change this time variable. So that would be the time. This is tau. Okay, tau. And as a d tau. So after this integral and the tau disappear, so you get what you want. So this is a general equation for this so-called linear response theory. So linear.
And F can be very complicated.
Well, there's no point to make F complicated in the first place.
I mean, in theory, though, like this is the general.
No. The basic idea is this stuff can be very complicated.
The chi.
Because that's chi is, how can you, without, for example, if you know, so in physics we have the good example. I can take the example for in physics we know that if you this is called N, it's called this is called the magnetization. That's a take example. This is very defined. Actually, these have a simple. This is formula in physics. Can you see? H is a magnetic field.
Yep.
So H is a magnetic field.
Yep. And this is just a product of chi.
Yeah, that's right. You can consider chi is just a coefficient.
Yep.
This is a good example. See, this equation 1 is general. So equation 2 is special for physics. Okay, this is called the magnetization. Magnetization. So what happens is that you can imagine that if this system is full of the randomly oriented magnet, okay? So without the disturbance, in this case, is a magnetic field. And the orientation would be random. So you would, so in this case, so in the absence, so obviously if 0 equal to 0, if H equal to 0.
Yeah.
Understand? Because are random oriented. So you wouldn't, magnetization is simply speaking, the stuff, it could be metal, could be alloy, become magnet, magnified, so it's magnetization. So this is clear, right? So this actually is a deterministic, okay? And actually it's, we can still apply equation 1, but in the textbook, we don't have to because this is a basic basic equation in physics. And this is a good example that how to we obtain this equation 1. Okay. However, so this is the key. Okay, that is so this idea is called. Do you remember the name? It's called
susceptibility.
Susceptibility. That's the key. Yeah, ability. So susceptibility is can be more specific, like originally introduced. in physics. Or susceptibility can be anything. You can start a psychological system, right? You got the perturbation, or sometimes the shock, right? But when this is quite different. Okay, I recently I get acquainted with a doctor from Chile, and we are going to have some talk online. But he basically started the neuroscience by detecting electrical signal. Mm-hmm. Now, from him, I've read some background before. I know something about that. But basically, they said in terms of treatment, people use a shock, electrical shock, to cure some mental disease. But this is not a linear response theory at all. This is beyond, because you got the shock, you shock, you actually reset whole system. Okay, you can imagine that if you got the shock, okay, in order to trying to, I wouldn't recommend people do that. You just reset. It's not a perturbation. So perturbation is perturbation. So therefore, that's why linear. So this is very keyword. This is air for linear. Why is it linear? Because we know that as long as there's a perturbation is small, is weak. We can always consider that response is linear. So that is why the response is linear. But of course, in the case of this shock treatment, actually there's electric shock, and that is not the perturbation anymore.
Is the linearness, if that's a word, is the linearity here analogous to the linearization when you're looking at stability? Is it a similar idea?
Well, linear approximation. Well, the linear population actually come from the Taylor series. So we have discussed Taylor series before. The Taylor series says any function x can be written as c0 plus c1x and plus cx squared and so on. Okay, that is come from Taylor series. Yeah. So there's good reason. If we just pretend nothing happened, which is unrealistic, so people wouldn't choose a constant. Okay, but we are dealing with the change. Yep. So therefore, the first step, the first degree of approximation is always used as a linear term. You see. Mm-hmm.
And is that the terminology? First, it's called a first degree approximation or first order.
Well. Zero order, first order is linear. Yes, first order is just use a constant. When you study physics, you know the perturbation theory. That is zeroth order. There's the first order. So this you can consider the first order. Yeah. The zeroth order. So there's first order. Yep. And the second order. Yes. Basically, that's why if you just stick with the form of Taylor series, you know that why we use the linear. Linear is the first step. So if you look at the history of optics in physics and in 60s, okay, at the beginning when Newton studied the light, they just simply use the light source available, right? And but then we after invention of laser, it's spontaneous, is much stronger. Millions times stronger could be than the ordinary light source. Now, in that case, if you still just pay attention to the first two terms of the Taylor series, you might miss a big pictures, right? Yeah. So that is why the nonlinear optics was born after invention of laser. So the nonlinear means that we cannot use linear series. After all, LR series, linear response series, is a linear series. Okay. Yep. Okay. Similarly, in the term of the electrical shock treatment, then you have to use the non-linear response theory. Okay, that's just terminology. Okay, that's terminology. Yep. And now people wouldn't stop here because, especially for theoreticians, and they have nothing to do but to just play with this mathematical ideas. Okay, so they wouldn't stop here. Actually, they got their in this. We don't blame everybody. If they're theoreticians, they can go beyond the simple original experiment. So basically, after a while, these simple relation. I'm still using this example in physics. So these susceptibility they have changed. So by the way, if this equation 1. And can we just write down, if you write in the frequency domain, so if you use O, but in the frequency domain, right? You will get the very simple relation. That is a chi, that's a susceptibility. And that is also the power spectrum of perturbation. So this is our equation 3, okay? So that is after Fourier transform. So the relation is just after FT.
Could you give me another example, or maybe even like a physical example of susceptibility, just so I can get an intuition for?
Oh yes, this is example. This example. So for the different materials, the chi is different. Can you see? For example, if you have different magnetization, for example, if you just write down can we just make some hypothetical experiment here? So if you do this magnetization experiment, then you basically we are studying the magnetization, which is measurable as a function of applied magnetic field, right? They all obey if a good approximation that they all is linear, right?
Yep.
But for the different material, you will see the different slope. Can you see?
Yep.
Some goes faster, some goes slower. Okay, that is why. That is why. And of course, they were eventually end with 0. And of course, things getting complicated if you just reverse the direction. I forgot that terminology. So they were not necessarily return immediately. There will be a lag of applied field.
Okay.
So, but my point here is that we look at this different color that could represent different material you used for this experiment, for this system. Okay, you change the sample. So that's the sample. When you do experiment, you can change the sample. So different sample, different composition, chemical composition, will give you different susceptibility. Similarly, if you return to the neuroscience. And different patient will respond the same stimuli differently. You see. I see. So you can use a reference. You see, for example, if you use just 2 I don't know, there could be 2 millivolt pulse, and for people, their response will be different.
Is that to say that, so in the general formula, in Formula 1, chi represents, the only term representing the system itself is chi?
Yes.
Susceptibility. Yeah.
It's not the system, it's also the susceptibility is that is a subject to something, okay, which is it's involved interaction, okay. And this equation allows you to treat this system as a simple, can be described as a single variable called chi. Now, if you do want to follow Newton's idea, there's no end, because if you use microscope, you can see that different parts have different structures, okay, and different structure is surrounded by different neighbors. So there's no point. So the reason we just use this equation 2 is that we just say, well, let's just assume that the connective behaviors of this of any material, magnetic property, can be described by a single variable called chi.
Is chi a scalar?
Yes, yes.
And is H like a scalar or vector? Or is it something fancy like a Hamiltonian or something?
Well, you see, because they both is good question, and both H and or sometimes use B, but here I prefer use H. That is a formula. H actually both H and M magnetization are vectors. Yeah, you are right. So so basically that is you can interpret this simple equation as how much percentage, what is the percentage of the the randomly oriented magnet, micromagnet, where change their direction so that they can become parallel to the applied field. It's natural, okay? It's natural.
Chi is just I'm thinking of Chi just sort of stretching space up and down.
Not that complicated. Chi is just like a response function, if you want to call that. So it's not response. It's kind of response mechanism. I just talk about, say, for example, your agent model also dealing with opinion, or public opinion, consensus. Is that, yes, if you constantly hear the report from media, from the government spokesman, and eventually that sky will change, right? They were very subjective. They have to digest the information and make their decision, right? So you see, this linear model can also be used to study the public opinion, the consensus.
Very general.
Yeah.
Yeah.
It's of course the stronger F, and the more people will be, the stronger the magnetization or stronger observation is.
Yeah.
Of course. That's what happened to China. If you constantly say this is good, it's bad, and people was born with these genes. Okay, you say, oh, at the end they just spontaneous, talk about something or speak about something for or against something, right?
Yes.
So yes, that's right. I think another you can apply this equation 1 to any area. Actually, that is why people outside physics found this simple formalism or ideas. So they're trying to. Do you remember that the second guy who got Nobel Prize in physics? Yeah, that's why I forget his name. But basically, he in the 70s he just introduced this idea, linear response theory for people in the climate change, meteorology, because in those days the meteorology is just follow this idea of the fluid dynamics. That's all. Okay, they know the clouds move and the temperature, pressure will balance itself spontaneous, and they just form the phenomenon called weather. But by the time they want to extend their scope of research to the whole atmosphere, they have trouble. So that's why that guy who got Nobel Prize, he was the first person to introduce this idea to this meteorology research.
I have one more question just about the magnetic example, because that's probably a simple example for me to ask a question about. So we've got the magnetization is a vector, chi is a scalar, and then we have the field is a vector, is another vector. What are sort of the parameters within H and M? Like, what is that individual?
H is what we call control. To understand, we're trying to simplify H as simple as possible, because there's no point. You see, for example, when you're trying to solve the problem, you always you use the perturbation. You wouldn't start with noise, right? You always start a sine wave or even the square pulse, okay? Because that is easy, analytically speaking, because you know the outcome, okay? You can do Fourier transform, okay? So this is something you have to learn when you want to do this research. You have to pay your attention to the things unknown instead of make the things controllable more complicated than necessary.
Simplify.
Yes. Okay. Yes.
And if so, it's interesting. So you said that analytically speaking, noise is the least tractable, but when it comes to modeling, is noise a lot of the time the first choice for, if there's some perturbation, you don't really know what it is, you just call it noise?
No. I think my point is this, that the perturbation, one thing is we try, in order to make the linearization valid, and or reasonable, we have to minimize. We have reduced the amplitude of the disturbance. On the other hand, the form of perturbation. I'm talking about the form of perturbation.
Yeah.
I wouldn't use noise, or I wouldn't use superimposed the sinusoidal wave in the first place. I would simply use a sinusoidal sine wave. Okay, and because that makes things so simple. So in this formula, we don't have to pay much attention to the mathematical form of the analytical form of the, in this case, magnetic field, right? Yep. Actually, it's constant. I tell you, in this experiment, the H is actually keep us constant. In this simple experiment, as shown in equation 2.
The field is a constant.
Yes. That's right, because we are interested to know the response of the sample to the applied constant perturbation. In this case, constant magnetic field.
Yep.
So when you start a complicated system, all right, and what you can see, this is actually a complex system is just the new. How to say, recall something we know before, long time ago. For example, if we want, for example, nuclear, it's too small, okay? We cannot see the nuclear. Okay. What we can do? Two approach, experimental approach. We just wait. We don't do anything. Okay. In this case, the perturbation is as external is 0. Okay. So we just let there happen. So we just let the. That's why people discover the nuclear radiations, alpha wave, gamma wave. Yeah, that's that's without, in the absence of perturbation. That's called the spontaneous nuclear decay.
Yep.
However, it's not enough because people want to know. So people use some perturbation, right? The perturbation, for example, they just sent for example, a neutron, okay, into the heavy nuclear. And for some nuclear which have limited mass and which or limited size as well, no response. If you just use a proton to collide with say the helium or the even use alpha ray, okay, to collide with the gold, for example, that was Rutherford experiment, and nothing would happen. We just slightly change the angle, change the direction of the incoming particle.
And that's different Fs. Different Fs.
In that case, you can say chi is 0. In this kind of experiment, you can say chi the susceptibility is 0 because there's how to say they don't care. It would appear the system don't care what this happened. However, if you're dealing with a huge, large nuclear like uranium, okay, and the chances that you will create the chain reaction, you will initiate the atomic bomb.
Right. Is chi always a function of F? You said they interact.
No. It's a property. You see, you have to categorize it. Is a chi is by definition is what would happen in the presence of the external perturbation. Okay. It's just the measurement, the metric of how system will respond to the external perturbation. It is a property. It is a physical property or chemical property of the material in this context.
But it almost seems to me like chi is a function of both F and the system.
Oh, no. F and chi are independent. If they are independent, if they are the same thing, if they are dependent on each other, then there's no point to define this equation 1. Obviously, you see F and chi are two different functions.
I mean, I can see it mathematically, but if chi is to a certain extent a property which changes for different Fs, is it not a function of F?
No, it's how to pick that. It's the internal property of the chi is the internal property of the material.
Okay.
which has nothing to do with the perturbation you used.
Okay.
And so it's just like the how to take the example, right? If it was yeah, can we imagine something which can give you an explanation? So basically, it's like a plant, right? Like a plant, it's a different plant have different resistance to the chemical fertilizers. Okay,
yep.
And probably some very plant, I don't know, but just hypothetical. Some, if you put very strong chemicals, they don't react. Okay, they still grow happily, but some vulnerable plant will immediately die. Okay.
Yep.
That is due to the internal capability, nothing to do with the chemical, you see.
Yes. Okay. So it's about the system. It's not about
the system. It's a property of system.
Okay. Yep.
And so it's just it's kind of ability to react to response the external change applied to the system.
Okay.
Now, this equation 3 is interesting because in this case, we can see that it would appear, so everything is in the frequency domain after Fourier transform. And in this case, and we have to edit something new, that is very famous relation. It's important to some name. Okay, I know you are good at pick up new names.
I love a good name.
Yes, let's say there's a very important name. Oh, right. He called. I can write down here. Yeah. Change the color. So that is a very famous relation. It's called the KK relation. Kramers, and another K is a Kronig relation. It's very famous in the context of linear response theory. So when if you want to use this idea in your writing, and that you must know this simple relation. It's not simple. I just give you the outcome. To prove this relation is rather tedious, right? Because basically, what do they have to? They have to in this case they will have make the omega into a complex number. So that complex, is that correct? Complex.
Yep.
Yeah. So the omega is not just the frequency we used every day, like we use AC, which is 50 Hertz. But in this case, we have to expand that domain of omega into a complex system. So basically, we have to in doing so, the chi also became complex number. So that is because of that, the chi will become complex. So that chi will become omega will become chi. That's how they do that. The real part and the imaginary part.
And does chi need to be transformed into the frequency domain necessarily because F is?
No. After Fourier transform, those theoreticians believe it would be useful, a benefit to consider this frequency as a complex number.
Okay.
And so hence that is the chi, the susceptibility become complex quantity.
Yep.
In this case, could be real. So in this case, at this originally chi could be the real. In this case, the real. Okay. At the beginning, this could be the real. So this could be the real at the beginning, but eventually they become complex.
Okay.
Due to the theoretician's effort, because theoretician is someone who want to dig out more information or mathematical form.
Yep.
So in this way, the susceptibility have become two parts. One is the real part, another is the complex part. Okay? Now, before I write the formula, I probably just, can we go to next page? So how do we deal with this complex? So this idea is complex susceptibility. Susceptibility. So how can we deal with this complex susceptibility, which contains the real part, the real part, and the imaginary part?
Yep.
Now, to cut the story short, I will just give you the result. Okay, I give you the result, knowing that they are the function of time of frequency. So basically, what we can do is can do this diagram. Then we will go to the equation. So basically, that will be the case. And the vertical is just this susceptibility. And the vertical will be the frequency, omega, all right?
Yep.
So basically, they say that if there's omega, if you choose omega for when you're doing experiment, you will control the frequency, okay? For example, this is your experiment control, this experiment control here. And in this way, you will see that something very strange now. So you will see the behavior of this imaginary. Can we start from imaginary part?
Yep.
Imaginary part will be give you this kind of the bump here. Can you see like Gaussians, right? Well, no, actually, Lorentzian. So that is an imaginary part. How about the real part? Can you guess? How about the real part? Can we use the green? How about the real part?
I'm just going to guess it's a very boring delta function.
No, it's not.
Okay.
It will be like this. So they will change that one.
Oh.
No, they're chasing that. Like this. So they are not dependent. Okay. So that's an important idea. So basically, so this is can we just label them so you can see this is imaginary part. That is a real part. Okay, real part is real. This is imaginary. Yeah, go on.
I'm just a little bit confused about the graph. So we've got the frequency on the x-axis.
Yes, that's the frequency. Yeah, that is the frequency you use when you use experiment. When you're doing can we use experiment? Particular frequency, yeah.
But is this the frequency of the system or the perturbation, or neither?
Good question. This is question. Let's just categorically say this is a system. This okay. I know is determined by the system.
Okay. Yep.
So experimentally we don't know, but we can scan, we can search, right? So when we do experiment, that is how to measure these two components, namely the real and imaginary part of susceptibility. So
that is to say, as the system, I mean, I'm sure this is a distortion of reality, but as the system's frequency reaches a higher frequency, its susceptibility decreases in the real domain.
Yeah. In the complex domain, the imaginary part reaches a maximum when these two frequencies equal. Yep.
When they're equal. I see. Okay. Yep.
Yeah. So if you take another example of the, that's why last year I did some consulting work for the local manufacture of some detector, water moisture detector, and in which that is equation is very relevant. Basically, in there, imagine that if you even talk about the atmosphere, for example, the solar system, solar radiation go from the sun to the earth, right? Then absorption will occur. Okay. In the meantime, as far as the wave, electromagnetic wave is concerned, the phase will change. So so basically this term, eventually this term, in the context of the micro absorption by vapor, by water, and this term will be associated with absorption. Let's just use.
And what would omega be in this context?
Can you write down here, absorption? Yeah, omega what?
Is that what our x-axis is? Omega, the W-looking thing.
Yes, omega. Yes, omega.
Yeah.
Yes,
what would omega be in this context of the radiation? Is that the radiation?
Well, radiation, the frequency of radiation can be adjusted.
Okay.
Adjusted. So,
yep.
So it have a certain there have a certain how to say, they have a certain distribution. But for that omega law, which is determined by the in this case is the water vapor. Okay.
Okay.
The moisture in the material, the amount or percentage of water in the material. You see, our atmosphere is not 100% dry. Okay, you can feel that, especially the moisture is getting higher, and which means that there are certain amount of water molecules in the air. So to cut the story short, similarly, this term can be considered as called a phase change. So this is actually physically detectable phenomenon. So in this case, I'm talking about this example. So that is micro absorption. So microwave absorption by water. Okay, by water. So, of course, this is a special example. In general, these two curves can be described precisely by two mathematical equations. It's not simple. I can copy that. I cannot remember. So basically, you can have two forms. Can we write as a final form, or do I use yep. So basically, I write down here. So the real part. So R for real part of this chi, which is complex number, right? Real part number can be written as integral, which is 1 over pi, and they have constant here, constant called p. The integral here, that from negative to positive. Just get something new for you to have a look, right? That is imaginary part. Actually, I prefer my notation because this getting complicated. I don't want to use imagine. I just use my notation for the prime and double prime for that one.
Yep. Is the relation here with the between the frequency and chi in the real and imaginary domains, is that relation with those two curves?
Yes.
Universal?
Yes. Yeah, it's universal. Yes.
Okay.
It's amazing. You see, by simply jump from the real number to the complex number, you got the universal relation. But bear in mind, this is valid in the linear response theory or under linear approximation.
Yep.
If nonlinear term appears, I discussed in my PhD studies. I didn't have much time. I just mentioned in passing that if the response is not nonlinear, the perturbation is not nonlinear, then this is called KK, Kramers-Kronig relation, will become invalid. You see. Okay. So that just bear in mind, this beautiful mathematical form are all only valid for linear response theory. Okay. Approximation, yeah, linear approximation. Yep. Okay, let's use my notation. I don't know, instead of letter R, I just use this is real part. I just use the chi. Can you see that is a simple? You see that's a real part. Can you see?
Yep.
That is in general, it's a function of omega. So I still use omega here. That can be written as the constant p. Forget about what the p is. They have they just write this here for. I will trace back to this p afterwards. But anyway, let me finish this integral. That is very beautiful. It's from negative to the positive. Okay. I think if you can use this equation, your instructor will be impressed. So that is why that's imaginary. Okay, in simple, imaginary is just this one. Double chi is called imaginary. Can you see? That will be divided by omega prime to be integrated minus omega. Okay, and symmetrically, we can write the imaginary part. Can you see? This is just like a pair. They have a certain symmetry.
Oh, and you just transforming between them.
Yeah, that's right. And no, they have very close. This is can you finish that? That integration is from positive to negative. Yeah, same range of integral, and this is very symmetric. Very symmetric. This is I prefer my notation here. So that is divided by omega prime. That's it. That's it. So if for example, you can if you have time, you can just use the Lorentzian function to represent this absorption imaginary part. Then you should be given that the phase change. Oh, another idea is called dispersion. Have you heard of dispersion?
No.
Dispersion.
Sounds like variance.
Well, it's just the magic is a fancy word. It's not a fancy word. It's actually well defined in physics. So that dispersion is kind of the something wave when wave interact with material, the phase were shifted. Not just the energy is absorbed by the material, but also the phase will be affected. And these two events occur simultaneously. So you can say, well, absorption occur. Okay, you can try to detect the attenuation. How to say? Attenuation. That is how much energy is lost, right? Or you can simply measure the phase change by measure the real part. Can you see? The first, this is the real part. This is real part. You don't have to measure how much energy absorbed. You just measure what happened to the phase. Then you can predict that absorption must occur at a certain frequency.
Yeah, because I was going to ask, like, what does the addition of the KK relation add to modeling? So in that sense, so like is in this context, the real part, like they refer to two different but equally useful types of susceptibility, so phase change and absorption, and you want to look at them separately.
Well, that allowed you to, just as I mentioned before, that allowed you to make your observation. You provided two options now. Okay. Now, if we just for example, if we don't know this KK relation, then we may have to measure the in this case magnetization, how much exactly, or absorption of microwave by water, how much. Okay, but with these KK relations, we don't have to, we say we don't, if the measurement is too tedious or too complicated or unreliable, then we can change to measure the phase change. You know what I mean? So it's complementary. This KK relation is very important because that provides with investors with kind of tools. Okay.
Yep.
And because of this basically K relation just Kramers-Kronig relation just indicate that you can actually treat this pair of susceptibilities components as dependent variable.
I see. And talking about susceptibility and perturbations and response, and I think I brought this up earlier, but it reminds me of some of the discussion which they went very briefly over early in the semester about concepts in dynamical systems like stability and Lyapunov stability and that kind of stuff. Is there any analogy between the two, or is it two separate things completely?
Well, you're talking about basically you're talking about a general case, okay? In that case, there's no series. There's they just it's over general. You are doing. You were told something very over general, okay?
Yeah. And
for example, you say, well, if the system is isolated system, or all of a sudden we're disturbed by the external, then what would happen? Okay, what would happen? But KK relation tell you exactly how can you monitor what has happened, and besides, it provides two options for you, depending on which is more reliable, which is handy for investors.
The tool. Okay.
Yeah, the tool, yes.
Yeah. Okay.
So actually, I can find some more precise diagram for it, because last year I did a lot of research for this guy. And then let's just show you some diagrams. It's good example to have some have a real diagram. So if I just go to the screen, I can go to the I can do some search. So what I'm going to do is a microresorption. Microwave. This one, can you see? Can you see this diagram here? I just
the real part looks like it's being flipped.
This is real. Can you see? This diagram. Can you see? The red one. Can you see? The red one is real part. Can you see? This is in the context. You see, this is called the permittivity. Permittivity is similar to susceptibility, but one is dealing with magnetic property, another is dealing with electric property. In this case, we are talking about the polarization, not magnetization. Okay, so you can see that the linear response theory can be applied in many areas. And but what you can see is that this is the reason you can see multiple stacked red curve, because they change the temperature, right? If you just focus on one temperature, can you see that? That would be similar to the diagram I drew. Can you see that?
Yep.
And also, is this how to say? Is this called what is the second? What is the point for the where the first second derivative equal to 0? What is the name for that point? Not a starting point, but inflection. No, what is that name?
Where no acceleration.
I forget that terminology. Basically, you can see this. Can you see my curves here? So when that at here, when the red color, when the red color reach to the inflection.
Inflection point. Yeah.
So that will correspond to the maximum of this blue curve, which is Lorenz's, or you can call it Gaussian's.
I see.
Okay. So this is a typical example that you can see. The reason we have different profile, because they use the wavelengths. I use frequency. That's why this You just go to that make my point. So can you see that? So that is how to apply the linear response theory in the case of the micro absorption.
With perturbations, you mentioned that linear response theory holds for small f for perturbation.
Yes. Yeah.
Is that to say that necessarily the system will, after the perturbation, the system, let's just say there's some system parameter going along and it gets perturbed, necessarily will it return because the perturbation was small?
No, that the process you mentioned is called relaxation.
Okay.
The process when systems spontaneously go from excited state, or which is unstable, right? Go to more stable state, which is what we call the ground state, or equilibrium state. This process called relaxation, and actually the time taken is called relaxation time, because you learn new two terminology here.
Excellent. So that's unrelated.
You understandably, any perturbation, unless you see, a good example is that unless you have destroyed, you have reset the system, right? Like you bombardment, you make the bombardment between the neutron and the uranium happen, and you will get a dramatic change. You get atomic bomb, right? However, if the perturbation is small, and also is not sustained. For example, the pulse, and the people get excited, but then eventually get relaxed, return. So spontaneously happen. Yeah. Actually, this is also related stop here. So this is also a very useful experimental method to start the how system can spontaneously return to the original equilibrium state, and that is how we can monitor for example, we can monitor the magnetization, and we will see once we withdraw the applied field, how long it takes to the magnetization reach to zero. Okay. So that is again. This actually that what I'm told you today is a physical method. People want to we are not in order to understand the property of unknown sample, right? We apply magnitude field. Okay, we can either apply at a constant value and change in step by step to see the response of or to measure this susceptibility. Or we can actually suddenly withdraw. Can you just because magnitude is generated by current unity. If I just suddenly switch off, the current will drop, and you will notice that something very interesting. So this is a very all I told you today is very useful for studying complex system. So basically, if you just imagine that you all of a sudden, so you have the applied this. Can we just this is you applied the magnetic field, right? But all of a sudden, because make sure you applied long enough, so therefore they got something. They had a sufficient amount of the magnetization which can be detected. That's magnetic field. But then all of a sudden you stop it. Can you see? So basically, so you apply the magnetization, and all of a sudden you stop it. You stop the applied field. What would happen to the? Can we just use just a single color to represent? So you can see there must be a process. For the magnetization built up. Can you see that?
Yep.
And then reach a certain amount, okay, stabilized. What would happen? They will just relax. Can you see?
Yeah.
So that is a good parameter for people to study different system. This curvature can be described exponential function, right? Depending on which material you use, and we can measure that constant. Do you know how to write it? So for example, m were equal to m null and E a constant. Can you see?
Okay.
That is a T. So this is a T. So sorry, this is time. This is time now. This is time. So that is you could so you can also measure this one. So therefore the different K. So this K is small. K is large. K is large.
Yep.
And K is small. So K is large. Other way around. This K is small. It decay faster. Okay.
Yep.
So if this guy, if they become permanent magnet, what would happen? Sometimes you can magnetize the metal, become permanent magnet. In that case, we can say that K is approaching to infinity. Okay, or zero. Sorry.
Yeah.
Zero. And it's so very fascinating. So that is why. So that is you see, complex system. No matter what it is, there are always established method to start a complex system. One is to monitor the change during the perturbation.
Yep.
Another is use the sudden switch, or you can imagine you can alternative. You can use a pulse. Okay. You can use a pulse. Actually, this is in my field. If you want to learn more, I will show you how do we start an electron spin by using this pulse to see spectroscopy.
Yes.
Spectroscopy. Yeah.
Yes. Awesome. Well, that's really good. I feel like I have a sort of a more general idea.
Yeah, don't worry. So we can, if you're interested, I can give you more methodologies well established to start any system, including complicated system, complex system.
Excellent. Excellent. That sounds great. Well, I look forward to it. Thank you very much.
Okay. You're welcome. See you next time. Goodbye.
I'll see you next time. Have a good day.
Take care. Goodbye.